Hi everyone, welcome to the live session. Today is the seventh live session, and unfortunately, I am taking it today on Friday instead of the coming Monday because I have to travel on that day, so I had to prepone the session. Really sorry for that, and it won't happen from next to next week onwards because we will be again meeting on. Um, Next month. Okay, so yeah, we will be again meeting on 28th of this month, right? So this session would have been conducted on Monday only, but I've preponed it and we'll be looking at the problems of assignment number 7. So from next week onwards, we will be looking at assignment number 9 so that from assignment 9 to assignment 12, you are able to look at this video so that how these problems are solved and you can take it as a reference to solve your current assignments. Uh, so today's assignment is very important because we will be walking through some of the these theorems which we use to solve the problems, the network analysis problems. Some of them are these Thevenin's theorem, Norton's theorem, then superposition theorem. There are a lot of other theorems, but we will be looking specially at these three theorems because these are probably the most popular and the most important, and you can expect many problems based on these, especially on Thevenin's and Norton's theorem. So, without further ado, let's start. I'll be sharing my screen. Just give me a moment. Yeah, I think my screen is visible now. And yes, okay. So let's start. So we will be looking at the various circuit theory theorems. So um, this will be, first we will be looking at Thevenin's theorem. So basically, suppose if we are given a circuit which is a linear combination of your EMF voltage source and these resistors and all the current drawing elements. So these are packed into this box, right? And then you have this load resistance RL. You have this kind of circuit. So using Thevenin's theorem, you can find what is the Thevenin voltage across this resistance and also the Thevenin resistance also across this terminal. So let's say this is terminal A and this is terminal B, right? So between or point A B. So between point A B, you can calculate your VTH, which is the Thevenin's voltage, and you can calculate the Thevenin's resistance. So there is a way to do that. We will look at some of the problems today. It will get clear. So finally, when you get these two values, your equivalent circuit something looks like this. So this is your VTH which you calculated, and the Thevenin resistance will be in series with this Thevenin voltage source. Okay, and this load resistance RL would be in series with your RTH and VTH. Okay, so this is your equivalent Thevenin circuit. Okay, so this is your equivalent Thevenin circuit. Now, um okay, so how to calculate VTH? So in order to calculate VTH, so we have this box, this black box kind of a thing, where we have all the important circuits and all. So in order to calculate, so first we are calculating the Thevenin voltage. Okay, so here we need to calculate what is the Thevenin voltage, right, across terminal A and B. So for that we need to open circuit RL. Okay, so open circuit terminal A and B. That means your RA will become infinite, right? Which means that your RL equals to infinite when you are calculating the Thevenin voltage. So you get some value of Thevenin voltage, right? So it's here it's VA, right? Now next comes your Thevenin resistance. So for this you have this box here, right, black box, and again you have this terminal A and B. Now what you do, you will look into this this circuit here, which this box consists of the of a circuit, right, which you will be given while you are solving the problem. So for while calculating the Thevenin resistance, you need to look into the circuit from terminals A and B, and then calculate what is your RTH. Okay, so suppose you are you have a circuit something like this. So let's say this is some voltage source Vx, independent voltage source. This is resistance. This is a resistance. This is a resistance, right? And let's say this is your RL. Okay, so this is, let's say, R1, R2, and R3. Okay, so most importantly, while you are calculating Thevenin resistance, while calculating RTH, you need to short circuit all independent voltage sources and replace them by their internal resistance or impedance, whatever you may say. Okay, so therefore here we assume that Vx has zero internal resistance, so it's an ideal voltage source. Okay, so therefore your Vx is ideal voltage source, right? So as a result, yeah, so you need to short circuit the Vx, right? That is what we read. So short circuit all independent voltage sources. So therefore you need to short this, and then you need to. So there was a, yes, that is an R2. Yeah. So this is a resistance. This is a resistance, right? And here, as we saw, that you need to. So let's say this is terminal A and this is terminal B, right? So while calculating RTH, you need to open RL, and then you need to look, while calculating, you need to look from this terminal. Okay, from this end, from point A and B, right? So this is what R1, this is R2, and this is R3. And here if you compare this with this, right? So this is your black box. So let me just use a different color. So this is your, this whole thing here, this is your box or black box. I shouldn't say black box because in black box you don't know what is actually going on. So this is a rather a box, okay, which consists of this kind of circuits. So therefore, mm, your RTH would be what? So simply, if you see here, for finding out the resistance, so you need to consider a current here I. As you can see, this I is getting divided into two parts, right? This is, let's say, I1 and this is I2. Therefore, you can, and this I1 is flowing through both R1 and R2. Therefore, your R1 is in series with R2, right? And its combination is in parallel with R3. Okay. So this is how you get, this is how you calculate RTH. So this is how you calculate RTH, the Thevenin resistance, Thevenin equivalent resistance, right? And here we saw that you how to calculate VTH, right? So basically, in this circuit, what we will do in order to calculate the VTH. So we have this circuit R1, R2. This is our Vx. So while calculating, just remember while calculating Thevenin resistance, you need to short circuit all independent voltage source, and also there is another rule here. So if I just put it down, so so this is rule number one, and rule number two is that if you are given with current source, so you need to open circuit all current sources, all independent current sources, and replace them with their internal resistance, so that should come in parallel with the path, right? So these are the two rules which you need to follow while calculating RTH. So here what we need to do, so we were calculating the Thevenin voltage from this point, right? So this was our terminal A B. So basically this is VTH, right? So VTH is nothing but VA, VAB, right? So this is pretty simple. So this is R3. Now if you calculate like this is I. Therefore, what will be your I? I will be Vx divided by R1 plus R2 plus R3, and VTH is Vx. So basically the drop across this resistance only. So R2 plus R3 uh, into R3. So basically this voltage divider rule, right? So this is how you get VTH. This is the basic step of how you calculate VTH and RTH in a Thevenin uh, circuit. Okay. Now we will also solve Norton's theorem. While we solve Norton's theorem, I will come across. I'll explain how to solve the problem. So let us now solve a simple problem and understand the concept behind Thevenin's theorem. Okay. So these are not assignment problems. I have collected it from the internet. These are some good problems which you can use, and I mean see solve on your own, and which will help you in the final exam, where, using which you can grab a certificate. So um, okay. So here I am really sorry for the small word. So I'll read it for you. It is written that find VTH, RTH, and the load current IL flowing through and load voltage across the load resistor in the circuit below using Thevenin's theorem. So we need to calculate what is the Thevenin voltage across this load resistance RL, and also the load current we need to calculate. Therefore, straight away you understand that you need to open circuit your RL, okay, which is of course 5 kilo ohm, right? So if you do that, what happens? It is a very simple problem. So I kept a simple problem so that you are able to understand, and then we go into the deep. So this is 12K, this is 4K. It is very similar to the problem that I just showed you. I mean the steps that I showed you moments ago. Right, so this is AB, okay. This is 12K, this is 4K, and this is 8K, and this is open because why we need to open RL, because we need to find out what is the Thevenin voltage across. It is clearly written flowing through the load resistor, right? So load resistor is nothing but RL, right? So we need to calculate what is the Thevenin voltage across this terminal. So it is pretty simple. You need, I mean, for calculating VTH, you need to apply simple circuit theorem analysis, right? So here, basically, here there is one single loop, single mesh, right? There is this you can't consider as a mesh because A and B are open. So here, if we cal calculate a I, right? Right. So this would be 48 divided by 12 plus 4 K would be ampere. So this would be milliampere, right? So this would be 3 milliampere. And what would be VTH? It is pretty simple. It would be, so since there is no current flowing through 8K, therefore terminal A here would be exactly this terminal, and terminal B would be this terminal, right? So therefore VAB would be nothing but voltage drop across 4 kilo ohm resistor, right, which is nothing but 4K into I, which is 4K into 3, 3 milliampere, sorry, right? So this would be volts. So this cuts off because milli is 10 to the power 3 and K is 10 to the power minus 3 and K is 10 to the power 3. So it cuts off. This is 12 volts, right? So your VAB is nothing but VTH. Why? Because you see here, VTH is nothing but the voltage across this terminal AB, and we just found out what is the potential difference across this terminal AB. Therefore, your VTH is nothing but AB. Okay. So this is how we calculate Thevenin voltage, right? This was Thevenin's voltage. Now going to Thevenin's resistance. So Thevenin, for calculating Thevenin resistance, we need to short circuit 48-volt source, right? So it's an ideal voltage source and it has no internal impedance. So therefore, the circuit would be looking something like this. then we have these resistances, right? So 12 is 4, and we have 8 here, right? So here we will be calculating RTH. This is 8K, this is 12K, and this is 4K. So what would be RTH if current flows through this 8K resistance? You will see that it gets divided into two parts, right? So this would be I1, this would be I2. Therefore, 12K and 4K are in parallel, and its combination is in series with 8K resistor. So RTH would be 8K plus its combination will be in parallel, right? So this would be our RTH. So what is the value? 8K plus 12 into 4 divided by 12 plus 4K. So 8K plus 48 by 16, so 3K, right? 11K. So this is our equivalent RTH. So we have calculated Thevenin voltage and Thevenin resistance. So this was question. These were two questions. So VTH is 12 volt and RTH is 11K. Now we need to calculate what is the load current flowing through this, right? So load current would be what? So what would be the Thevenin's equivalent circuit? It would be VTH. We just saw that the RTH comes in series with this. So VTH, RTH, and then of course this load resistance is there, right? So this is the load resistance RL, right? Which is nothing but, so RL is 5 kilo ohm. So therefore the current that would be flowing through this circuit is nothing but IL. So what would be IL? IL is VTH divided by RTH plus RL, right? So VTH is what? Just calculated, it's 12, right? And RTH is how much? It's 11, and this is 5, right? So this is 12 by 16 milliampere. So 354, and your load IL is 0.75. So this is how you approach a problem using Thevenin's theorem. So instead of this, you could have easily solved the problem. Or using two mesh, right? So this would have been simple mesh analysis. You would have had two meshes, right? So this would have been the first mesh. This would have been the second mesh, right? So there would have been I1 and I2, right? So this I2 would have been nothing but IL, right? So this is how you would have also calculated IL, but there you would have had two equations. Since this is a small circuit, so therefore you may find Thevenin's theorem not too, helpful here. But we will see later as the size of the circuit keeps on increasing. Now you will have more meshes, more nodes there. If you use nodal analysis or mesh analysis, that is KCL, KVL, your the number of equations will keep on increasing, and which will make this operation more complex. Therefore, in those scenarios, Thevenin's theorem is really useful. Okay. So that is the advantage of Thevenin's theorem. But anyways, this was a simple circuit, and this was how you perform the analysis. Okay, so now we will be looking at a much more complex circuit here. And again, sorry for today. I mean, the live session would have been actually on Monday, but I am traveling on Monday. That is why I had to prepone this session today. So we are looking at some of the important concepts of circuit theory analysis, which includes Thevenin's theorem, Norton's theorem, superposition theorem. And from next to next week, right, we will be again meeting on 28th of this month. That is on next to next Monday. So we will be solving two port theorems, which is your assignment number 9. I specifically chose this assignment because this was, this is very important, and these theorems will be required in probably in your two port theorems also. So that is why I chose this assignment, and we are looking at some typical problems today I took from the internet. Just a minute. Okay. So here, basically, so this is the second question, and this is a much more tricky question compared to the previous problem. And here you will see the importance of Thevenin's theorem or Norton's theorem. So we will be solving it both using Thevenin's and Norton's, and then we will try to verify the answer at the last. Okay. So here, see, you can easily solve this problem. So let's say the direction of I0 is this direction. So from left to right across this 6 ohm resistor. So here you can easily solve the problem using KVL, right? You have three meshes, but if you see, you have so many voltage sources and you have three equations. This will make the circuit more complex, where your Thevenin's theorem will come much more handy. You will be able to solve the problem more quickly. So here, I mean, let's start. So we will be first using Thevenin's theorem to find I0. Okay. So we'll be first using Thevenin's theorem. So as we know, we need to open circuit the 6 ohm resistor. Why? Because we need to find out what is the current flowing through 6 ohm, right? Therefore, we need to find out what is the, the Thevenin voltage across this terminal. We need to find out what is the Thevenin voltage, the Thevenin resistance, right? So once we do that, our Thevenin voltage, Thevenin equivalent circuit would become something like this, right? But this is RTH, this is VTH, right? And then we have this 6 ohm resistor connected at this terminal. So easily you can calculate what is the current flowing. So this would be I0, right? So I0 would be VTH by RTH plus 6. This is how you will calculate. So therefore, I mean, this is why you need to open circuit this the 6 ohm resistance here. So um, so let's redraw the circuit, and let's call this terminal A and B. Okay, so let me just use a different ink. So let's denote this terminals as A and B. Now let's redraw the circuit. Please be careful of the directions of this voltage source and current source while you are solving the problem, because this is important. So we will just open this, right, and of course then there is a 3 ohm resistor, then this voltage source. You will see how quickly we can calculate VTH here. Okay, so this is 8 volt, this is 3 ohm, this is 6 ohm, 12 volt, 6 ampere, 4 ohm, 2 ohm, and 3 ohm. So this is A, this is B, right? So what is VAB and what is RTH? Right? We need to calculate these two. So first calculating Thevenin's voltage. See here, we will again just redraw the circuit, or we will do it here only. So let's say we will use nodal analysis here. Okay, in this simple circuit, we'll use nodal analysis. Let me just use a different here. So let's say we ground this. I mean, we consider this as a reference terminal. Now, since this terminal is open, na, we won't. I mean, it won't be taken into consideration, right? So let's say just we consider this node as our node one. Okay. Therefore, see, if this terminal is open, therefore the current that is flowing from my reference on node 0, right, to node 1 is 6 amperes, right, and it is getting divided into two parts, right. So let's say this is I1. Now this gets divided to two parts, so this is I2 and this is I3. Okay, simple nodal analysis, and I hope you are clear with the reason why we are not taking this, because this is open, right? AB is open, because we need to calculate what is the voltage across these two terminals, right? This is open means there is no current flowing through it. So uh, your VAB, sorry. So if you apply KCL, so I1 would be equals to I2 plus I3, right? So I1 is 6. Now, what is I2? See, I2 is the current that is flowing in this node, right? And this is 10 volts, right? So, what would be I2? It would be V1 minus 10 divided by 2 plus 3, right? Because there are two resistances here. And what would be I3? It would be V1, right? Again, please don't take this into consideration. Please don't consider it as another node. Why? Because this is open, right? So therefore this is no node, because between this point, between A and B, there is no resistance, or there is no short circuit, anything. There is no current source, there is no inductor, capacitor, nothing. So you can't consider it as a node. It's open circuit, right? So therefore, this path from 1 to 0 via this 4, 12 volt and 6 ohm, this is a single path, right? So therefore, we can straight away write. So see here, this will be minus of minus 12. Why? Because the polarity is opposite, right? I mean, it's not facing I1. It is pointing from I1 to, pointing from node 1 to node 0, right? So therefore this minus sign is there. And here it was pointing towards I1, right? So therefore it was V1 minus 10. I hope you understand this. I mean, it's basic KCL concept if you have solved carefully those problems, right? And of course, divided by, there are two resistances, 4 plus 6, right? So therefore, our equation becomes, right, now simple. So this would be what? 2V1 minus 10 plus V1 plus 12 divided by 10. So this would be 60. 3V1 minus 20 plus 12, right? So this would be 3V1 equals to 80 minus 12, right? So V1 would be what? 80 minus 12 is 68 divided by 3. Okay. So I'll be just stopping here. Yeah. So if you guys have any doubt, you can ask till this point, especially for this problem. How we calculated V1, the voltage at this node. If you have any problem, you can ask. Because this is not assignment problem. This I have taken from the internet. Hello.
जी जी नो डाउट सर
Okay. Okay, fine. Then V1 is 68 by 3 volts, right? So um, see, it will help us to calculate what is VB and VA from here. That is why we calculated your 1. Now, what would be VA? So, till this point, what is VA? It is nothing but, see, it is pretty simple. Let me just use the different red color. See, till this point, right, till this point here, this is our VA, until this point here, this is our VB, right? So VA would be what? If we write VA is nothing but 8 volts plus the voltage drop across 3 ohm resistor, right? And your VB would be what? It would be voltage drop across 6 ohm resistor, right? So the how we calculate the drop, the current we already calculated using the nodal analysis. See, through this node here, I1 is only flowing, right? So therefore, what would be VA? VA would be 8 plus 3 into, see, since I1 is flowing from bottom, so from 0 to 1, so since current is entering, so I1 is flowing like this, right? So here plus would be here and minus would be here, right? Because when resist in a resistance, as you know, if a current flows in this way, therefore the terminal through which the current enters, that is denoted as plus, and the terminal through which it leaves, that is denoted as minus. So therefore, in this way, we can calculate what is the voltage drop across the 3 ohm resistor. So therefore, this would be minus 6 amperes. Why? Because see, clearly, right, this is 8 minus 3, right? Because this is pointing against 8 volts, simple. So therefore, this would be 8 minus 18. This is 10 volts, minus 10 volts. And what would be VB? VB would be the current that is flowing through, so I3 into 6, right? Because this is a single node. So I3 into 6, right? And there would be no minus, because see here, I3 is entering here, and basically this is plus and this is minus, right? So this is with respect to ground we are calculating. So this is VB. So what is What is I3? I3 is V1. We just calculated it's V1 plus 12 by 10. So V1 is how much? It's 68 by 3, right? And then this is 12, this is 10. So V1 is 68 plus 36 divided by 30 ampere. So this is 1404 by 30, right? So if I calculate, this is mm, approximately 3.47 ampere. So this is 3.47. Therefore, what would be VB? VB would be 3.47 into 6 volts, right? So this would be what? This would be 20.8. So therefore, your VAB would be what? It would be VA minus VB, right? Simple. So VA is minus 10, minus 30.4, right? So basically, if we write VBA, therefore this would be VA VB minus VA. So then it would be 20.8 minus or minus 10, right? So therefore this would be 30 points. So this is our VTH, right? This is our VTH because we open circuited the 6 ohm resistor and we are calculating the voltage, the Thevenin voltage across this 6 ohm resistor, right? So this is our Thevenin voltage. Okay. Now, so once we have calculated the Thevenin voltage, we will be now calculating the Thevenin's resistance. Okay. So what would be the Thevenin's resistance? See, so for Thevenin, calculating the Thevenin resistance, we need to follow this rule. So we need to short circuit all independent voltage source, and we need to open circuit all independent current sources, right? So therefore, if we follow these two rules here, um, basically if we redraw this circuit, it would be what? So there is a 3 ohm connected here. Then you have a 10-volt source. So you are short circuiting the 10-volt source. Now you also have a 3 ohm resistance here. Now there is a there is a, yeah, this is a current source, right? So this is a current source which is open circuited. Now you have this 4 ohm resistor and then a voltage source which is short circuited. So you have a voltage source which is short circuited, right? And this is the terminal. So you have a resistance here, you also have a resistance here, and this is 6, this is 3 6, and you need to calculate. So here basically you need to calculate RTH across this terminal, right? So what is the RTH? And this is 2, 3, and 4. So if we redraw this circuit, right, see, this would be what? So basically, here, see, here we have this 3 ohm. This is the 3 ohm, and then we have this 6 ohm resistor. Now with that we have these two, right? Um, 1 minute, just a minute. Yeah, so basically see here, if you see here, if you consider a current here, right? So you see that this current gets divided here. So this is I1, this is I2, right? And this I2 flows all the way. So this is open, there won't be any current flowing through this path. So this I2 would be flowing like through 4, 3, 2, and then returning through 3 back here. So therefore, your 6 would be this, then this is your 3, and then all the other resistances, right? So this is your 4, this is your 3, and this is your 2. So this would be the equivalent Thevenin circuit. So this is 4, this is 3, this is 2, and this is RTH. Therefore, what would be your RTH? This would be 6 in parallel with 3 plus 4 plus 3 plus 2. Hope I have done correctly. No, there is a mistake. There is a mistake. Sorry. See, I'll tell you why. See, um, as I was telling, so here this current is I. It is getting divided into this path, right? So this I2 is flowing through 4, 3, and 2 ohm. Then it is returning like this I2, and this I1 is also returning, and then this is again becoming I, right? So therefore, so this would be something like this. This is 3, this is 6, right? So this is 3, this is 6, and then here there are this 4, then 3, and then 2. This would be your equivalent circuit. Why, I'll explain again. So you need to calculate RTH from here. See, this is the from this terminal you are calculating RTH, right? So this is your current I. So for example, let's say that the current flowing through this path is I. So this is I. Now you need to see where the current through which path the current gets divided, because if our current gets divided in two paths, that means those two paths are in parallel, obviously, right? Because in a parallel two parallel paths, the current gets divided, right? In a series combination, current is same. In parallel, the current is unequal, right? We add the two currents. So therefore, this current I is getting divided into two paths, right? And since this is open circuit, and so this I2, it flows through these three resistances, and this returns like this here. This is your I2, and then through this 6 ohm also this current I1 comes, and then again it combines to form I. So equivalently, this should be your circuit. Okay. So therefore your RTH should be 3 plus 6 in parallel with 4 plus 3 plus 2. So therefore, what would be your RTH? This would be 6 plus 6 parallel to 9. Therefore, 6 into 9 plus 6 plus 9. So 45 divided by 50. So therefore, this is what, 15, right? Uh, sorry, this should be 54, and this would be 54. So this would be how much? 18. This would be 5. So 3 plus 3.6. Yes, this would be 6.6. Therefore, your RTH is 6.6 ohm. So I hope this is clear. So I hope this calculation of RTH is clear, how we arrived at this. Anyway, so now the application becomes really easy. So once we have calculated the Thevenin resistance, Thevenin voltage, now our equivalent So equivalent Thevenin's circuit would be what? This is our VTH, this is RTH, right? This is the equivalent Thevenin circuit, and this through this here our this RL is connected, right? RL or whatever you may call it, 6 ohm, right? So this is our 6 ohm. So through this we had to find out what is I0, right? Because I0 was the current that was flowing through 6 ohm. So therefore I0 would be what? I0 would be VTH divided by RTH plus 6. So therefore this is how much? This was 30.8. This is 6.6 plus 6. So this is 30.8 divided by 12. This approximately, let me just calculate, this is 2.44. So this is your I0 if you calculate it using Thevenin's theorem. So you can see that the problem is pretty, I mean not pretty, but it's lengthy to some extent, right? But it would have been more lengthy if you would have calculated this using not your KCL or KVL, because there are so many, in KCL if you use, there would be so many nodes, but in KVL there would be three mesh, but again you have so many voltage sources and one single current source, right? So it would make the circuit complex. Okay, so we will also try to solve this using Norton's theorem. Okay, so let me just explain Norton's theorem once. I hope this is clear. So if you have any doubt, you can ask. Okay. So in Norton's theorem, these are the two most popular theorems in circuit theory, right? So, uh, so let's say we are taking this circuit only, right? This box, and then which is connected to one resistance, right? So this is our box is connected to RL. Now to calculate what is the current which is flowing through this thing, so you need to first calculate what is the Norton's current, or we also tell what is the short circuit current. And this is the first criteria, and then the second criteria, so it is also represented as ISC because it is short circuit. Oh, sorry for the introduction. um, Secondly, we also need to calculate what is the Thevenin's resistance here. So it's the same as the approach to calculate Thevenin's resistance here also is the same as what we saw previously. But if you want to calculate the short circuit current, so you need to short this resistance here. Okay, so you just need to short this, and you need to calculate what is ISC. You need to short the RL, and then you need to calculate ISC. So once you have ISC, once you have RTH, your equivalent Norton's circuit would be something like this. So this is your ISC, what, RTH, right, in parallel, and then this is your RL. So basically your Norton's equivalent circuit is something like this. ISC, RL, sorry, RTH. This is your Norton's equivalent circuit, and if you have a load resistance connected, so this would come here. Yes. This is as simple as that. So you just need to short the RL, the load. So here also we need to short it, and then we need to find out what is the voltage, or what is the current flowing through this. So this is how we would be doing it. So rather than solving it, I am hoping that you solve it as an exercise. So basically what you will do here, if you are using Norton's theorem, so here so here this part would be shorted, and here there was a resistance. 2, 3, 4, so it's probably 10 volts, plus 8, 12. There's a voltage source here also. There was 3 ohm. Okay, so here you need to calculate what is the ISC. So you can easily apply a nodal analysis here again, right? So here you see, here there would be a node here. So here there would be another node 2, right? And this is node 0. So basically, if I won't solve it. You try it on your own. I mean, if you find out that your I0 is same as this I0, that is 2.44, you will understand that yes, your approach is correct. So let's say this is I, this would be again I1, this would be I2, this is ISC of course, right? And this would be I3. So you will have two equations, I1 plus I2, and then your ISC plus I2 will be equals to I3. And um, so your I1 you know, right? So I1 would be what? I1 would be 6 ampere. So here also there is another node. This is your third node, right? So these three nodes you need to consider, and then you need to find out what is ISC. Okay. So basically for this you can do something like this. So this is I3. Okay. So not 3. This would be I4. So your I4 would be I1 plus ISC, where your I4 is what? This is nothing but um, so V3 minus 8 divided by 3 ohm, right? So this is your I3. Then ISC, your I1 is what? I1 is 6 amperes. Then I2 is what? V1 minus V2 divided by, and here you also have plus 12, right? Divided by 4. Then I1 is, sorry, this would be I, not I1. This would be I. So this I1 would be uh, V1 minus 10 divided by 5. And lastly, your I3 would be uh, simple V2 by 6. So you need to substitute this, and this, right, in these three equations, and then you finally you will get what is the value of I, SC. So it should come to directly to 2.44, right? And then you have calculated what is the value of RTH, right? We already calculated it's 6.66. Therefore, your equivalent circuit would be something like this. So this is ISC, this is RTH, and this is your RL, right? This is your RL. So we need to calculate what is the value of I0. So this is ISC. So you need to apply the current divider rule. So ISC I0 would be what? ISC into RTH divided by RTH plus RL. So this would be your final answer. So I have given all the steps here. You just need to calculate and just verify whether you are getting 2.44 or not, because this is the correct answer. If you get it, you will understand that yes, your approach is correct. And if you are able to solve this problem, you will understand that yes, you are able to do understand Norton's problem as well as Thevenin's problem correctly. Okay, so I hope this is clear. So please try to solve it on your own, and the more you practice such kind of problems, the more comfortable you become, right? Okay, so let us now solve problem. Just give me some 2 minutes to drink water. Okay, so let us now solve the next problem, which is pretty interesting problem in the sense that here you have dependent sources, and your analysis here becomes not so straightforward, right? You just can't simply calculate RTH directly. Why, I'll tell you as we keep on solving the problem, this problem here. It is, I mean, in Thevenin's or in Norton's theorem, now you can, I mean, this dependent source wala problems, these are very common, and students tend to get confused. So we will solve a not too complex problem, I should say, here using dependent sources, right? So let us start, and we will try to complete today's assignment quickly. right? Okay, so here we have this one. This is 40 volt source. Now through this 5 ohm resistor we have this Ix, right? Now there is this dependent current source, right, which is flowing parallel to this 5 ohm resistor, you can see. And there is this, its value is 2Ix, right? And we have this independent current source of 8 ampere, and there is this 1 ohm resistor. Now they have told us to find out the Thevenin equivalent with respect to AB, right? So we need to find out the VTH and the RTH, right? So first, let us go on solving the Thevenin's voltage first. Okay. So for finding out the Thevenin voltage, AB is already open. So basically, your voltage. So this should be our VTH, right? So therefore, VTH would be nothing but VTH would be what? This would be I1 into 1, right? Because you can clearly see that this is, we need to find out what is the voltage drop across 1 ohm resistor, because AB is connected across 1 ohm resistor only, right? Simple. So, um, therefore, um, okay, so let us first calculate. So let us directly use KCL here, okay? So see, in this node here, we don't have any current flowing through it, right? Because here, this is a voltage source, right? We won't be having any current, so it would be supplying some current directly, right? So rather we can start watching. So let us mark like this. So this is node 1, this is node 2, right? And this is our ground, and this is also node 2 because there is no this thing, no resistance or voltage source connected across this, right? And this is obviously ground. So here we can directly start like this. So your Ix plus 2Ix, right? Because here this current is flowing and this is also flowing, right? And then here this is plus 8 because this is also coming outwards, and then this is I1, right? This is equal to I1. So directly you get this equation here, right? Now what is Ix? If we are able to find out Ix, we will get the value of I1. So what is the Ix value? This is nothing but, so Ix is nothing but V1. Sorry. So Ix is nothing but V1 minus V2 divided by 5 ohm, right? Because this Ix is flowing through 5 ohm, so basically the voltage drop connected across these two nodes across this 5 ohm resistor. So your V1 is what? Um, V1 is nothing but 40 volts, right? And V2 we don't know, of course, right? And okay, so let us just substitute. So we are substituting. So if I call this 1 and if I call this equation 2, and if we, so let me just pull it down. Okay, so substituting 1 in, sorry, 2 in 1, or rather let us call this one, right? Because this was in the final equation. Okay, so if we do that, then this is what, 40 minus V2 by 5 plus 8 equals to I1, right? So this is what 120 minus 3v2 plus 40 equals to 5i1. Right. So what is V2? What is V2? V2 is nothing but the voltage drop across this resistance, right? So V2 is what? V2 is nothing but I1 into 1. It is pretty simple, right? Because see, the node, the voltage across this node is V2, and here this 1 ohm resistance is connected between 2 and ground, and through this 1 ohm resistance, I1 current is flowing. Therefore, V2 is equal to I1. Therefore, we can directly substitute this here. So this is 3i1 plus 40 equals to 5i1. Therefore, I1 is what? 120 plus 40 divided by 8. So this is 20 ampere, right? This is 20 ampere. Therefore, your V2 would be what? 20 into 1 volt, which is nothing but your VTH, because this is connected between terminal A and B, right? So this is 20 volt, this is equal to VAB equal to VTH, right? So what is your RTH? Now we need to calculate Thevenin resistance, right? So, so we have calculated Thevenin voltage. Now what is Thevenin resistance? Thevenin's equivalent resistance. See, for this, um, what we will do, we will firstly short circuit the voltage source, short circuit all voltage source, and open circuit all current source, right? So correspondingly, what it comes, this is your, you will see there is a problem here. We can't really solve even this. That is why I am trying to tell this. So here is one. We can solve here. Obviously, this 8 ampere source is open circuited. That is why I am not drawing it. And this is RTH, right? This is RTH. Okay. So let us do one thing. Let us connect a voltage source, right? Let's say Vx here, with where this current Ix is flowing. Not Ix, sorry. Let's say this I1 is flowing. Okay. And let us not also call this as, rather let us call this as A. Okay. VAIA. That would be better. This is IA and this is VA. Okay. So let us call this as this. So see, what would be our RTH? This would be VA divided by IA. Why? Because this is the source impedance basically, nothing else. This is the source impedance. So that is why RTH is VA by IA. Now what is IA? IA is, so if we apply here, right, so what is the voltage here? It is nothing but your VA only, right, because this is connected across this only, so therefore the voltage across this resistance is VA. So VA by 1 plus, so there are two resistances, right? I mean, there are two paths basically. So basically your IA will get divided into this, and this, right? So basically three paths. One is VA by 1, the other is VA minus 0 by 5, and the other is minus 2IX. So this would be IX. Not this would be 2IX, right? This would be 2IX. So your it becomes what? VA plus VA by 5 minus 2IX. Now what is X? IX. So IX is, because IX is the current flowing through this path. So what is IX? IX is nothing but Vx by 5, VA by 5, and of course minus, because why minus? Because our current direction is in this direction, right? But Ix is flowing in the opposite direction. That is why this minus is coming here. So therefore you can directly substitute it. So VA plus VA by 5 minus 2 VA by 5, right? So therefore it comes as this thing. Therefore this would be, right. So therefore your IA is what? 4 by 5 VA. Okay. Um, just a minute. Yeah. So therefore, what would be your RTH? Your RTH would be VA by IA. Therefore, it is 5 by 4. So this is how you can calculate circuit these dependent sources, because these are dependent on current flowing through resistance, or maybe in a AC circuit, maybe capacitance or inductance, right? So this while we are short circuiting or open circuiting voltage source or current sources, these are independent current sources, independent sources, but these are dependent sources. You can't short circuit or open circuit it. So that is why what you need to do, you need to apply one voltage source here, and the I mean imaginary voltage source. So VA is imaginary voltage source. Okay. And you need to so if you apply voltage source, there would be a current flowing. So finally you calculate what is the source impedance, or the impedance or the resistance of the source, of the voltage source, which is nothing but its voltage divided by the current flowing through it, right? So this is how you calculate RTH. Okay. So yeah, I hope this is clear, right? So we will probably be looking at one last problem for the day, because I know it's already overloaded. Uh, so we will be looking at one last problem, superposition problem here. These two problems I am not solving. Uh, I mean, you can. It will be there. These are assignment problems, so I am intentionally not solving it. because you might have already gone through it, because we are running 1 week late, right, in this. So that is why I was planning to solve assignment 8 today, but due to, I was in a hurry, that is why I couldn't sit with that. So that is why uh, we are looking at some important circuit theory concepts, nothing else. So we'll be looking at assignment 9 from the next to next week onwards. We'll be up to date. So if we solve assignment 9, it will help you to solve the current assignment problems. Okay. So yeah. Okay. So lastly, we come to this concept of superposition principle or theorem. So what is superposition? Let us quickly see here. So let's say we are given this voltage source, okay, and let's say we have this two, three resistances, and we have a current source here. So let's say this is I1, this is V1, this is R1, this is R2, this is R3, and we are told to find out what is the current which is, let's say, flowing through, not through R3 rather. Let's say we're finding out what is the current which is flowing through R3. Okay, so what is I? We are told to what is find out what is the value of I, that is which is the current flowing through R3. Now here you can directly apply mesh analysis. It is simple because the circuit is small, but we can also solve it using superposition theorem, and this is how. So here you see we have two independent current sources. Sources. One is voltage source and another is current source, right? So we have two independent sources. Now uh, we need to consider one at a time. So we need to consider one independent source at a time. Okay. So let's say considering V1, that is the independent voltage source. So when we do that, if we have other sources, so if we have a voltage source, right, another voltage source, so let's say instead of I1 we had another voltage source V2 here connected. So we need to short circuit all other independent voltage source. Okay, so this is one. And if we have current source, so we need to open circuit all other independent current source. Similarly here, so if we are considering I1, same thing would get repeated here. Okay, so basically if we are considering V1, we saw that we need to open circuit all other current sources. So therefore this would be your equivalent circuit, right? See, this R2 is there, but this is open, right? Therefore there won't be any current flowing through R2, right? So this is I. So let's say this is I1, right? So what would be I1? This would be V1 into R3, voltage divider rule, right? R1 plus R3. This is your I1. Now, once you are done, you need to consider I2. So we saw that uh, when we are considering, I mean, in superposition principle, we need to short circuit other independent voltage source or open circuit other independent current source. So here, while we are considering I1, we have another independent voltage source which we need to short. So we are sorting this, right? In the rule we saw this is R3 and this is R1 and this is I1. So this is R3, this is um, R2 and this is R1. Right. So what would be, so let's say this is I2. So what would be I2? This is simple current divider rule. So this is would be what? R1 plus R3. Therefore your I would be I1 plus I2. So this is how you solve uh, I mean any problem using superposition. Why I1 plus I2? Because see, by both the times when we were considering either one voltage source or the other time one current source, so the current that was flowing through R3 was always pointing in the downward direction. That is why, and our fundamentally initially our initial current was also pointing towards downward direction. Therefore, this is I1 plus I2. Simple. Okay. This is a simple superposition theorem. So, having done that, let us now solve this problem quickly. Okay, so considering 10-volt source first. So if we do that, we need to open circuit 12 ampere source, right? So this would be what, and of course this is open because we open circuited the current source. Yes, this is how we do, right? So this is 6, this is 3, this is 2, this is 4, and let's say this is I1 dash, let's say this is I2 dash, let's say this is I3 dash, and let's say this is I4 dash. Okay, so we will be using nodal analysis here because we need to find out every current, right? So here this is one node, this is another node, and let's say this point is grounded. Therefore, directly if we apply, see this is one current. So what in the first nodal equation, what would be the equation? So I1 dash would be equals to I2 dash plus I3 dash. So what is I1 dash? It is 120 minus V1 divided by 6 equals to V1 divided by 3 plus V1 minus V2 by 2, right? So if we solve this equation, this would be uh, okay, sorry, yeah. So there is one mistake. Um, yes, I couldn't see at the first instant. So see here, since there is no node here, right? For this problem, there is only one node, right? Because this node 2 doesn't matter. Why? Because this I3, because this part is already open, right? There is no current source here. So this I3 would directly go downwards. Therefore, we can write I3 dash equals to I4 dash. It is pretty simple because this is no node, right? So this would be what? This would be 120 minus V1 by 6 equals to V1 by 3 plus V1 by 2 plus 4. Simple. So 120. I mean this you will know provided you have solved nodal analysis carefully because it's a very important. KCL and KVL are the two most fundamental concepts of circuit theory analysis. If you know that well, then only you will be able to master these theorems properly. So this would be 6, right? And how much this would be if we simplify this? This would be 2V1 plus V1, right? So this this would be 120 minus V1 by 6 equals to 3 V1 by 6. This will get cancelled, and this would be 120 minus V1 equals to 3 V1, therefore 4 V1 equals to 120, therefore V1 equals to 30. Right? This is V1. So once you do that, you can easily calculate what is I1 dash. Right? What is I1 dash? It is 120 minus V1, which is 30, divided by 6. So therefore 15 amperes. Right? What is I2 dash? It is nothing but V1 by 3. Right? V1 by 3 through this 3 amperes this thing. So this would be 30 divided by 3 would be 10 ampere. Then what would be I3 dash? It would be V1 divided by 6, right? So this is 5 ampere, and this is also equal to I4 dash, because this is the current that is flowing, right? So this is the first part. Now coming to the second part, that is we are considering 12 ampere source, right? So now we'll be considering 12 ampere source. So therefore it means that we need to short circuit that in 120 volt source. So the equivalent circuit would look something like this now. And what I am doing here is carefully see. This 12 ampere source is pointed downwards, right? So I am just pointing it upwards with minus 12 ampere. So essentially it is the same, right? It's just the same. There is no difference. I'm just pointing it upwards with a negative sign. That means it is actually pointing downwards. So therefore, let us say that the current that is flowing through this 4 ampere is I4 double dashed, okay? And we are considering it in this direction because the current is flowing in this direction. So let us say this is I3 double dashed, this is I2 double dashed, and this is I1 double dashed. Okay. So now here clearly we have two nodes, right? Why you can easily, I won't explain, you easily know that. So here this would be minus 12 equals to what? So basically this current would be equals to, so this is getting divided here and here, right? So minus 12 equals to V1 minus V2 by 2 plus V1 by 4, right? So this would be 2V1 minus 2V2 plus V1 by 4. So minus 48 equals to 3V1 minus 2V2, right? Now this is the first equation. Now in note 2, what it would be, so at here, what would be the equation? It would be what here, V1 minus V2 by 2. So here this current is flowing and it is getting divided into this part. So basically your I3 double dash equals to I2 double dash plus I1 double dash. So I3 double dash is V1 minus V2 by 2, and I2 double dash is V2 by 3, and I1 double dash is V2 by 6, right? So V1 by 2, this would be what? Uh, 3 V2 by 6, right? So this would be 3, 3, 3 gets cancelled. So V1 equals to 2V2, therefore V2 equals to V1 by 5. So this is our second equation. Therefore no, um, substituting 2 in 1. Okay, so if we do this, then minus 48 equals to 3v1. Uh, Sorry, this would be 2, right? Minus v1. Okay. So v1 would be what? Minus 24 volts. v2 would be what? Minus 12. See, this everything is coming in minus. Why? Initially we, this is inverted, right? I mean, this is pointing downwards, but here we took it as minus 12. I mean, it's pointing upwards. That is why this minus. Due to this, everything will come in minus. Okay. So therefore, what would be your I4 double dash? It would be V1 by 4, right? V1 is how much? 6 minus 24 by 4. So this is minus 6 amperes. Then your this was I4 double dash, right? That means this thing. So then I3 double dash would be what? It would be V1 minus V2 by 2. So minus 24 minus or minus 12 divided by 2, therefore minus 6 amperes. Then I2 double dash would be what? V1 by 4. Sorry, not 4, right? I2 is 3. It is V2 is how much? Minus 12 by 3. This is minus 4. And I1 is finally V2 by 6. Therefore, minus 12. So now we need to calculate what is I1. So let us first calculate I1. So carefully see in the first figure, I1 is pointing in this direction, right? So I1 dash was what? So basically, if you consider the directions, right? So here initially while we were calculating with 120 volts, right? When we open circuited 12 ampere source, so I1 was pointing from left to right here, I1 dash, but I2 dash is pointing towards the from right to left. So therefore I1 minus I1 double dash, right? It is simple. So therefore this would be what? I1, yes, 15, and this is minus 2, right? So minus or minus 2. I hope this is clear. This is pretty simple if you consider the directions. In the same way, your I2 was what? I2 was pointing in this direction. I2 here it is also pointing in this direction, and here also it is pointing in downward direction. Therefore, your I2 would be I2 dash plus I2 double dash. So this was probably 10. Yes, and this was therefore 6. Then I3 is what? In the original figure, it is pointing in this direction here. Therefore, I3 minus I3 double dash, right? So therefore, this was 5 minus or minus 6. This is 11 amperes. Finally, I4 is how much? I4 is again pointing downwards in both the cases, right? So this here, here, and here. So I4 is I4 dash plus I4 double dash. Therefore, this is 5 plus minus or minus 6. Oh, minus 1. Okay. So while you are solving this problem, so you must be really very careful about the signs, the directions, because that would confuse. If you make a mistake in any of the step, it would create a chaos, and then you won't be able to find the correct answer. Okay. So this is how you solve superposition principle. So there are two more principles: compensation theorem, Taylor's theorem. I haven't solved it because if you solve the circuit analysis problems, you will find that these are the three most important problems, theorems that you come across, and this would be useful in two-port network analysis also, which we'll be solving next to next week. Okay, so I will be uploading this video by tonight, sorry, and we will be meeting again next to next week, that is on 28th. We won't be meeting on 20th. Please be mindful of that because this is a preponed session. The session on next Monday I'm taking on today, that is on 17th at same time. So please don't join on Monday, there won't be any meeting. Therefore we'll be again joining on next to next, and we'll be looking at assignment number 9. Now, if we solve assignment number 9 of the previous run, it will help you to solve the assignment number 9 of the current run. Okay. So please go through these problems, and yes, also try to solve this using Norton's theorem and verify the answer. Right. This is a pretty good problem. It's a pretty good problem that we solved today. So yeah, that's it for today. Uh, so if you have any doubt, then please do comment on the YouTube channel. I will be uploading this video, and we will be again meeting on 28th of this month. Thank you very much. Have a nice day. Good night.